Welcome to MFC Group's Fast Tech Seminar Series hosted by EAS Sales, FH Sales, Mel Foster, and TMC. We appreciate you joining us this morning. Today we are featuring RBSOA, SCSOA, and the deadly area in between with Littelfuse. Our speaker for this seminar is Dr. Martin Schultz, who is the Global Principal Application Engineer for Littelfuse. Martin has more than 20 years experience in the industry, a PhD in power electronics and electric drives, and even has several patents in the fields of power semiconductors. So we're in good hands. Everyone is muted, so please type any questions you may have into the meeting chat. We'll be sure to monitor those and answer them at the end of the presentation. And then please be sure to stick around to the end. We're going to do a fun round of trivia, which will be a mix from the presentation and some general trivia, and the top 3 winners will win a prize. So with that, Martin, I will turn it over to you.
Thanks, Amanda, for the introduction and the kind words you spoke. So welcome to this presentation, and you'll quickly see what the acronyms RBSOA, SCSOA mean, and what is the deadly area in between. All the considerations and presentation details were gathered from a special power semiconductor, the MDMA 280. However, the content is true for literally all IGBT-based technology. So what is it that destroys power semiconductors? So particularly this is the picture you don't want to see, at least not too often. The major cause is mounting and thermal issues. And within the thermal issues, there is the so-called power cycling in minutes, which is applying bursts of power to the devices for a longer period. And the same thing happens in seconds as well. So these 3 things either gradually degrade the devices, which is the power cycling effect, which also accelerates aging and finally leads to destruction. Or in case of bad mounting habits, it could instantly destroy the device as well. The missing fraction for the pie chart is covered by overcurrent events and overvoltage events. And then comes the RBSOA effect. RBSOA is reverse biased safe operating area. And then there's a spooky part missing, and that's cosmic radiation. That's not Darth Vader or Captain Picard topic. So cosmic radiation isn't science fiction, it's science. And all of these effects lead to instant death, to instant destruction of the devices. And most of them can be, well, at least reduced in effect or even prevented. So why is this presentation important, or is this topic important at all? And yes, it is. From the field, we got experience with particularly the module that is featured. And this module holds a rectifier and a brake chopper. So taking a look into the destroyed device, you can clearly make up the 6 diodes that form the grid side rectifier, the freewheeling diode, which was still intact, and the IGBT from the brake chopper, which was destroyed. The customer claimed that this IGBT was turned off well below short circuit levels, and it happened over and over again. So being reproducible and being within specification, it's a module-based issue, and please, Littelfuse, go and solve this for us. That's an important question to ask. Is it operated within specification? To clarify, it's helpful to take a look at what a semiconductor is usually suffering in specified ranges of operation. That is based on voltage, current, switching losses, cooling performance, and all those can be predicted to allow continuous operation. You'll find reasonable data in the data sheet for those devices, like, for example, collector current, and each collector current comes with a case temperature. So naming a current without giving the thermal conditions is typically not a good idea. That depends on the thermal resistances, both from the junction to case and from case to heatsink. And throughout the operation, this particular device is limited to 1200 volt. Exceeding this level of 1200 volt, even for short term, potentially even transiently, leads to destruction. So these are maximum ratings not to be exceeded. And where does this transient phenomena come from? And that's a part that happens when you turn off a power semiconductor, potentially or particularly an IGBT, because the setup will always feature some stray inductance. So if you have the IGBT turned on and the stray inductance is in place, that's not an issue. However, you want to turn the IGBT off again, and you want to switch from one instant to another. And if you look closely what happens on the IGBT, you can do this by a so-called experiment double pulse testing and then check what happens. If you turn the IGBT off after the current flows, the current will go from the instantaneous value down to 0. The voltage on the other side will be 0 when the device is turned on, because then it's literally the saturation voltage of fractions of 2, potentially 3 volts, depending on the device. And at the end of the switching, the voltage reaches the DC link level. However, and that's the trouble, in between, there's a current change rate. And if you apply a current change rate, di over dt, to an inductor, it leads to an additional voltage. And this voltage spike definitely has to remain below the breakdown voltage of the device. This overshoot, this delta that becomes visible from collector to emitter, that's why it's called VCE, depends on the stray inductance and the current change rate. Stray inductance will always be there, and the current change rate is something that tends to be as high as possible because it reduces switching losses. So here is the core of the trouble. You cannot eliminate the stray inductance, and you need a high-speed switching event. So that's the transient phenomena that has to be considered. The regular operation is given by parameters like junction temperature, blocking voltage, maximum current. And here too, you'll find data in the data sheet that helps you. And that's the RBSOA, the reverse biased safe operating area. And you can see that it's giving information about the junction temperature, 125 degree, not to be exceeded. The collector emitter voltage, 1200 volt, not to be exceeded. 300 amps, also not to be exceeded. And that all by given gate voltages and gate resistances. So putting this into a diagram with collector emitter voltage and collector current, there's a maximum voltage. In this case, it's 1200 volts. There's a maximum current, 300 amps. And the shaded area is the so-called reverse bias safe operating area. As long as operation takes place in this square, the device operates in a specified area and behaves as predicted. So now and then, events outside of this area need to be considered and to be handled. And exceptionally, that's short circuit. So short circuit is an event that is limited in duration. And of course, the short circuit current is much higher than the current that the device is rated for. So here too, you'll find datasheet information for the short circuit safe operating area, or SCSOA. And you can see that there's a short circuit duration. So short circuit has to be terminated in 10 microseconds or less. The short circuit current is expected to be in the regime of 450 amp. And here too, the maximum voltage may not exceed 1200 volt. The 450 amp, given that this is a 150 amp device, is a common value which results from the fact that IGBTs are limiting the short circuit current to about 3 to 4 times the rated current. And they're mostly specified to withstand this condition for 10 microseconds. So if you trigger a short circuit using an IGBT, the diagram you obtain looks like this. So If you turn it off within 10 microseconds, you're fine. The voltage across the device is not going down simply because the device desaturates. And you can see that the short circuit current grows to 460 amp in this measurement. So the 450 amp of the datasheet are pretty well met. So how does this all add up? And that's easy if you give an overview for comparison. In the diagram where the device is rated with a voltage and a current, the device has a rated current of 150 amp, has a maximum current for IGBTs, typically twice rated current, and that spans the reverse biased safe operating area. And then there's a short circuit current, which in case for this module starts at 3 times rated current. From here onwards, we're talking about the short circuit safe operating area. And there's a gap in between. And that's the forbidden area. In this area, switching is not allowed. And that's an important statement. So in the RBSOA, the IGBT is saturated. There's charge carriers to carry current, and the world is fine. In the short